you can actually get better performance out of batteries made from recycled material than from virgin materials.
We're at the point where we're leaving the lab and entering commercialization.
This is very high value material. No one's going to want to throw it out.
From smartphones to electric vehicles to stationary power storage, lithium-ion batteries run much of our modern world. But we've got a big problem on our hands when these energy reservoirs wear out, especially in a world where EVs are pervasive. These battery packs are bulky, loaded with rare materials, and, up until now, extremely difficult to reprocess. In this video, we'll explore the current state of lithium-ion battery recycling, learn how it's done and why this is important, and we'll touch on what all this means for the electric vehicle world. Now, it's still relatively early days for all of this, but dozens of companies around the globe are tackling this looming problem head on.
Battery recycling writ large for lithium-ion batteries is about a $3.5 billion, with a B, billion-dollar business. They're expecting it to grow something on the order of 22% to reach about 23, almost 24 billion by 2033. The circular economy is based on lithium-ion battery recycling. They seem to have the basics down to this point.
I think overall there's a lot of technologies, a lot of companies developing recycling capabilities. Most are either at bench scale or early pilot stage in North America in particular. There is recycling in China and in Asia overall. That's functioning today, but in North America, we're really just starting to build out this infrastructure to recycle lithium-ion batteries.
If you've ever visited the comments section of our videos, you might be picturing vast acres of EV batteries littering landfills. Fact is, that's just not the case, at least not yet.
The challenge with recycling right now is that there actually aren't very many batteries, or not nearly enough batteries to recycle as we would ultimately want. Because we're still relatively early in the EV transition. So most, probably 85, 90% of all the EVs ever built have been built in the last 5 years. And those vehicles are still in service and probably will be for most of them probably for at least another 5 to 10 years, if not longer. So the batteries in those vehicles are not ready to be recycled yet.
And so it's kind of a chicken and egg problem. In order for battery recycling technology to scale up to an industrial level, companies perfecting the processes need grist for the mill. However, combustion-powered cars and trucks still vastly outnumber electric vehicles in the US today, which explains why there's a dearth of batteries for companies to recycle. Compounding this, modern EVs are also proving to last a lot longer than many people expected.
We found that Tesla's Model S and X batteries are amazingly robust. They were built to last 7 or 8 years. Many of them have gone 10 or even 12 years without a really significant loss or degrading of capacity on board, and they'll continue to work.
With expectations adjusted, experts now foresee the first wave of long-range EV batteries to be ready for recycling in the next 2 to 3 years. It's fantastic that some vehicles are going the distance, but this is not ideal for reprocessing companies, especially as they're struggling to scale up. Fortunately, though, there's another big source of lithium-ion battery materials that can be recycled, one that many people are not even aware of. I mean, I didn't even know about this. Though to be fair, I'm not that smart, so it really shouldn't be a surprise.
Cell manufacturers will make batteries for cars, and in that process, they produce scrap. Typically, any cell manufacturer has a target of about 10% scrap.
Wait, what? 10% of the materials intended to go into a lithium-ion battery are just junk? I mean, it's not exactly the same thing, but could you imagine if 1 out of every 10 engines or transmissions an automaker built were broken? It'd be the Ford PowerShift automatic.
10% is a very aggressive target. I think early on, a lot of these cell manufacturers will have much higher scrap rates. So if they're making 100,000 tons of lithium-ion batteries, 10,000 tons of that will end up having scrap that needs to be recycled to go back into the loop of production. So that scrap would be processed by Aqua Metals, for example, and go back into making PCAM and then CAM material and then back into the cell manufacturer to make the cells out of it.
CAM, C-A-M, is an acronym for cathode active material, and it's the precise combination of minerals and chemicals that make lithium-ion batteries work. PCAM, importantly, is precursor cathode active material, a powder-like blend of these various elements that birth a new battery. Now, at the battery end-of-life stage is the wicked-sounding black mass. And, well, it definitely is the problem child to be dealt with here. Black mass is the shredded mess of cathode and anode materials from a used battery, and that's what recyclers will have many thousands of tons to deal with in the near future. Unless EVs don't break or something, and then they won't have to. Or if they just dump them in the ocean, that's an option too. A lot of people don't consider ocean dumping.
And so we think it's very important to make sure we get this right on the recycling side. And so we did get into the lithium-ion battery recycling space a little later than most, but it gave us the benefit of being able to evaluate the approaches that other companies were taking. And we saw some really key challenges, mainly around chemical use and waste streams that derive from that chemical usage. And so we designed a process that doesn't produce any waste streams. And we reuse the chemicals that we do use. In other words, we recycle the chemicals themselves. Our technology is the most sustainable in the industry, and we think it's got a great economic advantage as well.
In a minute, we'll get to the unique Aqua refining process David just mentioned, but first, a few battery recycling basics, because there are different ways forward, each with advantages and, of course, disadvantages.
There are two main ways to recycle a lithium-ion battery. One is pyrometallurgy. The other one is hydrometallurgy. Pyro is generally shredding the battery to create a black mass and then burning it. And once it's cooled, you go in and you try and recover what minerals you can. But that means you have to go back and refine those minerals before you can use them again. Hydrometallurgy skips that part. And essentially, you shred to create the black mass. You then leach the active materials you're looking for out of the black mass using various solvents. The ease of use is really the appeal to hydrometallurgy, along with the percentages recovered. Pyrometallurgy yields about 60% of the source battery's content. Hydrometallurgy yields somewhere over 90%. Usually the number seems to be hovering around 95% recovery rate, which for a recycling operation is unheard of. We don't even get that much aluminum back from recycling aluminum cans.
The process of recycling can actually recover about 95 to 98% of these materials, and also the copper and aluminum foils that make up the base of the cathodes and anodes. Pretty much all of the key materials, the most expensive materials in the battery, can be recycled. And that's important from a sustainability standpoint, from an energy use standpoint, getting those materials back instead of having to mine raw materials all over again.
Pyrometallurgy is not a good option for recycling lithium-ion batteries. This process is energy intensive, produces tons of noxious fumes and carbon emissions, plus some of the materials you're trying to capture basically burn away the lithium and manganese, according to David. The hydrometallurgical process is superior, but it's still far from perfect.
What this does is it uses up a lot of chemicals. They consume the chemicals as they use them. And a byproduct of this is called sodium sulfate. And this is going to be an enormous issue. Even in the CAM manufacturing industry, for every ton of CAM produced, you're producing 10 or more tons of sodium sulfate that has to either get landfilled or put into the ocean. And in hydro or hydrochemical recycling, you produce about 2 tons of sodium sulfate for every ton of black mass recycled. So essentially a hydrochemical recycling facility is really a sodium sulfate manufacturing facility with a byproduct of nickel and cobalt and lithium.
According to Aqua Metals, their Aqua refining process is vastly cleaner and more efficient than the recycling techniques used by rival companies.
But the challenge with going right to the sulfates is, one, the sodium sulfate waste stream, and two, the hydrochemical process has real challenges in getting to purity levels that they need to get to be battery grade. Our process is a bit of a hybrid of hydrochemical and electrochemistry, and we take the black mass, the ground up batteries, and instead of precipitating out with chemicals and producing like a nickel sulfate, we actually produce nickel metal and cobalt metal through electrolysis. We plate out high purity metal, and we produce lithium hydroxide and lithium carbonate.
But how do you selectively pull each specific material out of the same solution without making some giant mess? Well, that is the secret sauce, just like ranch dressing on a Reuben.
Metals plate at very specific conditions. So if you begin to separate the black mass while it is in solution, that solution is going to have a variety of other elements in it that you don't want. And then you put it into a plating cell, and you plate that metal under very specific pH and voltage conditions. And it pretty much only plates that metal, leaving behind the other contaminants.
You can actually get better performance from batteries made from recycled materials in some cases, because each time you recycle it, you're actually getting more refined, more purified minerals that you're putting in there. If you're taking virgin materials, the process of refining and processing that, you will be taking out a lot of the impurities, but there's always going to be something left in there. It's not huge gains, but every little bit helps. And if you can have an extra % or two of energy density, energy capacity with the recycled materials, that's potentially a % or two of battery that you can reduce. You can reduce the weight of the battery, the size of the battery, and that all has a cascading effect on the overall efficiency of the vehicle. If you can cut down the size and weight of that battery, the vehicle doesn't have to do as much work. You can get more range with the same size battery or a smaller battery.
Numerous companies around the world are developing lithium-ion battery recycling capabilities or are expanding their operations. Here in the US, we have one dominant player, at least for right now.
The 400-pound gorilla in battery recycling is J.B. Straubel's Redwood Materials. J.B. Straubel, as most of you know, is one of the founders of Tesla. Redwood has started to build a couple of new campuses dedicated just to recycling cells. One of them is in Tahoe, Nevada. Big surprise. They'll take scrap from the Tesla facility in Sparks, Nevada, recycle it, and give it back for reuse in the Sparks facility. I'm told they're also taking other manufacturers' scraps that could possibly include Lucid, which will soon have its own battery facility in Queen Creek, Arizona. So we can watch for a pretty robust facility being established in Tahoe, Nevada.
Arguably, I think Redwood Materials is at, an early commercial scale at this point. They are taking in batteries, reprocessing them, and then selling those materials back to Panasonic for use in the cells that are being produced at the Tesla Panasonic factory in Reno, Nevada. And they also have partnerships set up with Volkswagen, Ford, Volvo, and I think a couple of other OEMs now.
According to Sam, about 50% of the old batteries Redwood Materials currently recycles come from consumer electronics, though the company has signed deals with numerous automakers to repurpose their manufacturing scraps and end-of-life batteries. Additionally, Conrad said the company is also opening a massive new recycling facility in South Carolina, one that's capable of producing up to 100 gigawatt hours of cathode from recycled materials. But will this be enough?
We're expecting to have a terawatt of cell manufacturing in the US by 2030. Our estimates say that if all that gets built by 2030 and everything's running, everyone meets their timelines, we're looking at about 1 million tons of battery scrap that needs to get recycled. And I can tell you now that the recycling industry will not be there. It will not have scaled enough to support that. Now, timelines will shift, and maybe we don't get to a terawatt by 2030, but either way, there's a lot of scrap coming that will need recycling. And all the OEMs are going to want that recycled because it's valuable money that they have some, capital into.
Whether the industry is ready or not, we need a robust domestic battery recycling system in place, preferably sooner than later.
What we don't want to do is be reliant on virgin materials. Some of them, like cobalt and to a lesser degree nickel, there simply aren't enough reserves of those materials in the ground to use just virgin materials, to rely entirely on virgin materials. We're going to have to use recycled materials at some point. If we want to have 100% EVs, we are going to be producing multiple terawatt hours, somewhere probably on the order of 8 to 10 terawatt hours worth of batteries every year to meet production requirements. And a 100 kilowatt hour battery pack requires about 66 kilograms of nickel if it's an NCM battery. And so the amount of nickel that's available, it just isn't there to support those kinds of production rates. So we will have to recycle or find other types of materials to use.
As mentioned, it's still early days, but the experts I spoke to seem optimistic about the future of lithium-ion battery recycling. This nascent industry is just getting off the ground, but it seems poised for big growth in the coming years.
I think this is the right move at the right time. Giving someone time to think and plan for a future and see how things work operationally is always better than rushing in to solve a problem that is still occurring.
We have a pilot that we've been running since December of 2022, and we're currently under construction for our phase 1 commercial facility, which will process 3,000 tons of black mass. First black mass will go in and commissioning will begin mid this year. And our campus for that facility will scale to 10,000 tons of black mass processing the next year or two. There are other companies, as I mentioned, that are in development of technology. I'm not sure of their throughput plans, to be honest, but I think we're still at very early stages in terms of an industry in setting up a recycling infrastructure.
That infrastructure is more than just developing the technologies and building the plants that will enable full-scale reprocessing. Once we've solved the chicken and egg problem, new challenges will arise and new business opportunities along with them.
As we go forward and we actually do have larger quantities of batteries to be recycled, towards the end of this decade, early into the 2030s, then the problem becomes a little bit different. And that is, how do we collect all these batteries and get them to the recycling facilities? So in the case of the consumer electronics batteries, it's pretty straightforward. They're pretty small. People, can take, drop off their phones and other lithium-ion battery devices into these drop boxes. It's easy to collect those. But 1,000, 1,500, 2,000 pound, or in the case of GM, 3,000 pound battery packs, a little more challenging to get those and get them distributed to the recycling facilities. And so one of the things that needs to happen is we need to build a business model around how we collect and aggregate and transport these batteries to the recycling facilities. Because there's obviously a cost associated with that, and so there's a lot of work being done around that idea.
As for an apocalyptic wasteland dotted with depleted batteries, when your current or future electric vehicle eventually reaches the end of its useful life, there's no need to worry about its power pack being trashed. Recycling can harvest the critical materials inside and put them to good use again, and do it with minimal pollution. Like the unexpectedly long life cycles of some of the earliest Tesla batteries, EVs keep surprising us. So when we recently went to a Nissan facility to deep freeze an Aria, I would have rather deep fried it, but they wouldn't let us do that, we were prepared for anything. And you're going to want to see what happened to the driving range when we held this car below zero for 16 hours. Click over here to witness the full saga. There was no crispy breading, and I'm still upset about it.